If gravity varies as a dampened wave function, the immediate question is it possible that the other forces might do the same thing? The strong force, the electromagnetic force, the weak force. Is it possible that these forces also might vary in this fashion and that it's been missed? So today I just want to speculate on that a little bit. The strong force is what holds the protons and neutrons together in the nucleus. I want to speculate a little bit about that today, and also about the electromagnetic force. What the implications might be if these forces also behave in a similar. What follows does not have any experimental basis or proof. It's really more or less a what-if speculation. Let's compare what I was saying about orbits, applying the same idea to particle physics in the atoms. Now, these pictures are greatly oversimplified. So, electrons are not really like planets orbiting around the sun. They're not really like that. Instead, they spend their time in various orbitals, and here I've depicted a few of those. And the orbitals really describe the probability of finding the electron in this area. So although it's not totally like, or it's not even at all like a planet orbiting the sun, we still can apply the idea of the force varying as a wave. One common question that gets asked is, why don't the electrons ever collapse into the nucleus? Since the electrons have a negative charge and the nucleus has a positive charge, why don't they just simply collapse into the nucleus? In fact, this does sometimes happen, where a proton captures an electron and then the proton changes and becomes a neutron. But why does this not happen more often? We're lucky it doesn't, by the way, because then all matter would be neutrons, and the processes allowing life would not ever take place. Before answering that question, I'd like to make a small digression to talk about antimatter. In 1928, Paul Dirac did something that no one had ever done before. He predicted the existence of something which had never before been seen in nature. He predicted the existence of the positron, which is just like an electron, except it has a positive charge. This has come to be called antimatter. In antimatter, things are reversed. So in antimatter, it is supposed that in the nucleus is something called an antiproton that has a negative charge. Neutrons stay neutrons. And positrons are supposed to orbit this antimatter nucleus, just like electrons orbit a regular nucleus. But what if a positron is not some exotic form of matter? What if the positron actually always exists in the nucleus, and a positron is really just a constituent of normal matter? I'm proposing a structure for subatomic particles that looks something like this. I introduce something called the subneutron, which is truly neutral but never exists alone. It is always bound up with a positron, or else an electron, or else both. So this would be what the structure of a proton is. It's a subneutron tied up with a positron, and the positron is always present in the nucleus of regular matter. Then this would be what a neutron looks like. It's got both an electron and a positron tied up with the subnucleus. And this would be what antimatter is. Well, I should say this is what an antiproton is, where you have the subneutron tied up with an electron. But why introduce this structure? The goal here is a simpler version for the structure of an atom. If each of the fundamental forces, the strong, electromagnetic, and the weak forces, also reverse polarity at various distances, in other words, if they're sometimes attractive and sometimes repulsive, and this varies with distance, then particle physicists may be able to come up with a simpler model that does not involve positing quarks. What if the strong force operates on an electron differently than it operates upon a positron? What if at the distance of a normal electron orbital, like let's say this first orbital here, the strong force attracts a positron, but it repels the electron? This would mean that an electron would have something of a barrier to overcome, and overcoming this barrier is very rare. This is why electrons are not often absorbed into the nucleus of. A particle physicist once explained to me that they've looked to see whether neutrons and protons are polar or not. That just means, is the charge located more in one place or another? And they find that it's not polar. So for this hypothesis to be true, one of two things must be going on. Either the charge, like the positron or the electron, either the charge is moving around super fast so that it can't be localized, or else when they combine with what I'm calling the subneutron, then they must form a totally different structure or totally different particle where the charge is not localized in one place in that particle. Leaving aside the strong force for a moment and thinking just about the electromagnetic force, I did think of an experiment that we might do to see if maybe the electromagnetic force, the electrical force, to see if that reverses at certain distances. I think if we take a very strong magnet and then we go out to distances which physicists aren't really used to testing. Normally all these kinds of tests are done at pretty close distances, but if we take electric charges or ions at a very far distance and see how they behave in a magnetic field, we might find that at certain distances they reverse the direction of travel. But whether or not the electromagnetic force reverses, however that works out, it may be true that the strong force affects electrons and positrons differently, and it might be true that the positrons are just part of the nucleus of normal